Physics 101, Lesson 1. Things change. Some changes are physical, some are chemical. A chemical change is one where the substances undergo a rearrangement of the atoms and molecules through how they are bounded. Physical changes are changes of position, time, orientation, image, shape, and other such physical actions which manipulate the substances. It is, therefore, important we ask what motion is. Approximately around the year 500 BC, philosophers were wondering what everything was made from. Thales said that everything was water. Heraclitus said fire, which he meant constant change, and stated that nothingness is, and everything is becoming, meaning changing to their next thing. A constant changing nothingness. Parmenides reversed this idea, and said that nothingness is not only not a thing, it's also so much not a thing that we cannot even think about it. Parmenides then went on to state that change constitutes a momentary nothingness, as A becomes B, but is not yet B, but is no longer A, and that this was not possible, and therefore the universe was full, unchanging, static. That the appearance of change was an illusion. Parmenides' student Zeno defended this claim that things don't change by creating an argument against motion. Zeno argues that to move across a room requires first moving halfway through the room, but to move halfway requires moving a quarter of the way through the room, and this pattern continues on forever. The point of the argument is that if we try and make point A and point B discrete places that are not the same place, then there must always exist a discrete place, point C, between A and B. In fact, there are an infinite amount of places between A and B. Zeno therefore argues that motion is not possible, as to get from A to B first requires passing through an infinite amount of places in between the two, and this compounds as it remains true no matter how close you move B to A, so long as B is not A itself. Motion, therefore, is the act of going from point A to point B by traveling through point C, which exists between them. Even if Zeno is correct in some higher dimensional or different dimensional world or whatever woo we want to pretend, what we experience in reality is motion of objects. Things really do change location from time to time, and in fact, they change locations in time. Over an elapsing period of time, the objects are changing position. Even when we leave an object on the shelf for a whole year, that object, with the rest of the Earth, was changing locations, making a full loop over that year. To go from rest to motion requires a change in speed, called acceleration. And when that speed is not changing, we call it velocity, if we know the direction and speed. If we don't know or don't care about the direction, we just call it speed. So to change positions, we need to accelerate to a new velocity, one which is not zero, which takes time. A change in position is called displacement and is written delta x equals x final location minus x initial location. A change in time is called elapsed time and is written delta t equals the final time minus the initial time. A velocity is a rate of change in position over a change in time in a direction and is written vector v equals delta x over delta t, which equals the final location minus the initial location divided by the final time minus the initial time. and note the arrow on top of the v, which indicates a known direction. An acceleration is a rate of change in velocity over time, and is written vector a equals the change of vector v over delta t, which can either be the final velocity minus the initial velocity over the final time minus the initial time, or can even be written as the final location minus the initial location divided by the final time minus the initial time squared. We can graph this change using a vertical and horizontal line representing the change in the units involved. Average velocity and acceleration. Both of our formulas for velocity and acceleration are currently better suited for averages, and are not helpful for a particular point on the curve, as the change in time would be 0, and so the velocity or acceleration at any particular point is a change of position divided by 0. Was Zeno correct? Every time we think we have a velocity, and we check our velocity at point C, and not the average over A to B, but specifically at that one single moment at time and space, the change in time is 0. The velocity is impossible by this equation. Sir Isaac Newton saved us from Zeno by studying change, and inventing calculus to solve this divide by 0 Zeno problem. Instantaneous velocity and acceleration. When we find the velocity of an object at a single moment in time, we call that the instantaneous velocity. The instantaneous velocity is the limit of the average velocity as the change in time approaches 0. The instantaneous velocity equals the limit as delta t approaches 0 of delta x over delta t. This means that the slope at that point represents the velocity at that point. The same is true of instantaneous acceleration, such that instantaneous acceleration is equal to the limit as delta t approaches 0 of delta v over delta t. Motion diagrams. A diagram maps out the entire history of the object's motion to which we are interested or concerned, and as such is one of our best ways of understanding motion in general. One-dimensional motion diagrams. One-dimensional motion graphing diagram. The acceleration at point C can set the initial time to 0, and therefore the instantaneous acceleration can be written as a equals the final velocity minus the initial velocity over t. We can thus rearrange this equation to find the final velocity. By timesing both sides by t, we get at equals final velocity minus initial velocity. So moving the initial over to the other side, we have an equation that solves for the final velocity. Final velocity equals the acceleration times time plus the initial velocity. For example, if a car starts with a velocity of 2 meters per second to the right, and then accelerates to the right with an acceleration of 6 meters per second squared for 2 seconds, then after those 2 seconds, the car's final velocity is, plugging this into our equation, final velocity equals 2 meters per second plus 6 meters per second squared times 2 seconds will get us 14 meters per second to the right. The car's final velocity is 14 meters per second to the right. Given that the final velocity equals acceleration times time plus the initial velocity, imagine what happens when a is constant. A constant acceleration times time is the instantaneous final velocity at that point in time. And therefore, when and only when a is constant, is it true everywhere that the average velocity is the final velocity plus the initial velocity divided in half. From this mean average velocity of final velocity plus initial velocity divided by 2, we can get position again by multiplying time to both sides. The velocity times time equals 1/2 times time times final velocity plus initial velocity. which is actually the change in x. From our final velocity, we can also find the equation for time, such that time equals final velocity minus initial velocity divided by a. We could also plug in our final velocity equation into our new delta x formula, and we find that delta x will equal 1/2 times acceleration times time squared plus the initial velocity times time. Or we don't plug in the value for the final velocity, but instead solve for the final velocity with this formula. As such, we will get v squared equals 2a times the change in position plus the initial velocity squared. So here we can find the instantaneous final velocity without time, and assuming a is constant. So altogether then we have 1. Final velocity equals initial velocity plus acceleration times time. That is velocity as a function of time. 2. Delta x equals initial velocity times time plus 1/2 the acceleration times time squared, which is the displacement as a function of time. Or 3. Final velocity squared equals 2 times the acceleration times the change in position plus the initial velocity squared, which gives us velocity as a function of displacement. If we turn x into y, we can find the position of falling objects. The change of y equals 1/2 acceleration times time squared plus initial velocity times time. By breaking the change in y into final y and initial y, we can move the initial y to the other side and find the final height equals the initial velocity times time plus 1/2 the acceleration times time squared plus the initial height, where in this case a is the gravitational pull. A equals negative 9.8 meters per second squared. Examples. 1. The nerve impulses of the human body move at approximately 100 meters per second. If you stub your toe, how long will it take the nerve signal to reach your brain? 2. A person takes a trip, driving with a constant speed of 89.5 kilometers per hour, except for a 22-minute rest stop. If the person's average speed is 77.8 kilometers per hour, A. How much time is spent on the trip? And B. How far does the person travel? 3. A graph of position versus time for a certain particle moving along the x-axis is shown in the following figure. Find the average velocity in the time intervals from A. 0 seconds to 2 seconds, B. 0 seconds to 4 seconds, C. 2 seconds to 4 seconds, D. 4 seconds to 7 seconds, E. 0 seconds to 8 seconds. 4. An attacker at the base of a castle wall 3.65 meters high throws a rock straight up with a speed of 7.4 meters per second at a height of 1.55 meters above the ground. A. Will the rock reach the top of the wall? B. If so, what is the rock's speed at the top? C. Find the change in the speed of a rock thrown straight down from the top of the wall at an initial speed of 7.4 meters per second, and moving between the same 2 points of elevation. D. Does the change in speed of the downward moving rock agree with the magnitude of speed change of the rock moving upward between the same elevations? Explain physically why or why not.
Okay, let's do an example. 1. The nerve impulses of the human body are approximately 100 meters per second. So if you Stub your toe. How long will it take the nerve signal to reach your brain? So, step 1. What we want to do, step 1, put S1. Step 1. We want to draw a picture. Picture. Stubby little arm. This is you. So, your height is whatever your height is. We are going to take an average. The average height, according to the internet, for human beings in general is, let's see, where did I get it? Is 5 feet 7.5 inches. And we stub our toe, and that signal gets sent. Let's assume a straight line up to your head at a velocity of 100 meters per second. We need to convert 5 feet plus 7.5 inches into meters. The conversion, let's see, yeah, I got it written down. The conversion between meters and feet is 0.3048 meters per feet. Feet cancel. Plus 7.5 inches times 0.0254 meters per inch. That gets us 1.524 meters plus 0.1905 meters, which is a total height then of 1.7145 meters. So we will just put that. H equals 1.7, just round up to, say, 1 meter. Step 2. Let's write down what we are given and then what we are missing. Given, we are given our height, 1.71 meters. We are given the velocity of the nerve. I can make a better N than that. 100 meters per second. What are we missing? Well, we want to know how long it will take. So we are missing time. Time is a question mark. And that's all the information we have. So, step 3, find an equation that relates the given to the missing. Well, height is actually the change of y, and the change of y has an equation where if you were to take it over the change of time, you could find velocity. Therefore, if you times both sides by a change of time, you can find out what the height would be by traveling a certain distance for a certain amount of time. So then you could divide both sides by v and find out that the change in time is equal to the distance you move divided by how fast you move it, which makes sense. So then, in short form, this is our equation. Step 4, solve. Plug these values in. So t equals h 1.71 meters over 100 meters per second. That fraction makes the second pop to the top. So I'm going to say seconds. And then 1.71 divided by 100. T equals 0.01? Yes. 0.171 seconds. So that's how fast then it takes for the nerve from your foot to reach your head, given this height. You get to put in your own height. Question 2. A person takes a trip driving with a constant speed of 89.5 kilometers per hour, except for a 22-minute rest stop. If the person's average speed is 77.8 kilometers per hour, A, how much time is spent on the trip, and B, how far does the person travel? Since the person driving has a constant speed, we're gonna first draw a picture of several dots moving at a constant distance, such that ... Another one here. That this will represent having traveled 89.5 kilometers, and we will track it on an imaginary timeline, such that at the start, at t equals 0, then at t equals 1 hour, we traveled that many kilometers. So we have an even spacing. Then we stop, say after hour 3, we take a break for about 22 minutes and then continue on our way. So our total trip would then be divided up into 3 segments: driving, stopping, driving, and our average would be this unit here. Let's call it x1 plus x2 plus x3 divided by 3. That would get us our average, right? Something like that. But alternatively, not as realistic, but nothing against it in the rules, let's assume that our 22-minute break just comes in at the very end. So we do the whole trip, then we take a break. Then we know that the total distance traveled, the change of x, will simply be 89.5 kilometers for every 1 hour times x, well, let's say, times r amount of hours. And then, actually, let's say m, because that will be our moving. Because then we take a rest, r, of 22 minutes, having moved 0 kilometers. So then the average, let's go into given, actually. Given. This gives us an average velocity of 89.5 kilometers times m plus 0 over, say, the time moving amount of minutes plus the time at rest amount of minutes. We know what the time at rest is. That's 22 minutes. 22 minutes out of an hour is 0.36 hours. That's 0, so we don't care about that. This is alternatively just the change of x. The change of x is equal to the velocity time, the velocity of the amount time moving, let's call that Vm, times the amount of time moving. So the velocity times the time gets you its distance. Makes sense? And we know what Vm is. So our average actually is Vm Tm. That actually then gives us an equation. So let's just clean this up. TR equals 0.36. Missing. Our missing is our x. And our time moving. So the values that we have here, time moving, every other number we have. So in step, well, that gives us our equation, so let's actually just jump to step 4 and let's solve this. The average is 77.8 kilometers per hour equals, we have here the moving velocity, 89.5 kilometers per hour times Tm over Tm plus 0.36. So what we can do here is we can take the denominator times the denominator by itself on this side. What we do to one side, we have to do to the other. So another way of saying, we can, in a sense, cross multiply. This is times 1, that's times Tm. So 77.8 times Tm plus 0.36 equals 89.5 Tm. So that gets us 77 Tm. Just get rid of the bracket there. And then 77.8 times 0.36 gets us, what does that get us? It gets us 28.526 repeating 6. So we can move the 77.8 to the other side. Subtract both sides by 77.8 TMs. And we get then, I'm just going to move up. Get 28.526 repeating. That's in hours technically. And that is, what is that, 11.7. 11.7 TMs. So then TM is 28.526 over 11.7. And our time, therefore, is 2.438. It carries on for a while. I'm going to call it there. Hours. So we can even round that up. That is 2.4 hours. So then that is just the time moving. So the average was 89.5 times 2.4 over 2.4 plus 0.36. Therefore, for question A, the total amount of time total, is 2.4 plus 0.36, which is about 2.8, right? Because 4, 5, 6, 7, I got 7, 6, rounding up 2.8 hours. How far does the person travel? Well, we only care about this. We don't care about that part. For B, the velocity, that's the change in distance, is 89.5 kilometers per hour for 2.4 hours. So the change in x is therefore, let's see, approximately 218 kilometers. Stop the lapel, stopping the phone, stopping the camera. Question 3. A graph of position versus time, position, time, for a certain particle, so the particle is this line, it's moving along the x-axis is shown here. We want to find the average velocity in these time intervals. So from 0 seconds to 2 seconds, so from here to here, from 0 to 4, from here to here, from 2 to 4, from here to here, from 4 to 7, from here to here, and from 0 to 8, from here to here. So we start, obviously, at A. The average velocity, so the average velocity is the change in time, x final position minus x initial position, divided by the final time minus the initial time. So in this case, we have x changes from, let's just put the time interval first, actually. Time interval is from 2 seconds, that's our final time, 2 minus 0. And the positions, the final position at 2 seconds is 10. And the initial, when t was 0, was 0. So we have 10 over 2. That is 5, we're doing meters per second. So A is 5 meters per second. B. Same equation, different time interval, different x. So when the times are 4 seconds and 2 seconds, at 4 seconds we have, this is at 5. And at 2 seconds, it is at 10. So we have here 2 seconds, 4 minus 2, that's a difference of 2 seconds. 5 minus 10, that's a difference of minus 5. So we have negative 5/2, or we can say negative 2.5 meters per second. So the negative here will tell us that it's going in a different direction, the opposite direction, in fact, which we can see by the graph. It was traveling positive x and then turned around. C. The change of time for C is, actually, this is wrong. That should have been 0. Let's just go back. Let's just go entirely back. Okay, B. The velocity for B is at a time interval of 4 seconds and 0 seconds. 4 minus 0. At 4 seconds, we had continuity error. Continuity errors. So many continuity errors. Okay, let's do B. So the velocity for B will be at 4 seconds minus 0 seconds. 4 minus 0, which obviously that is 4 seconds. And at 4 seconds, this was at 5 meters. And at 0, it was at 0. So that is 5 meters, which gets us a positive 1.25 meters per second. All right, C. C is from 4 to 2 seconds. 4 minus 2, which is 2 seconds. And at 4, we had 5. But at 2 seconds, we have 10. 5 minus 10 is negative 5. So this gets us negative 2.5 meters per second. This negative, for the velocity, indicates the direction of motion. So when we were going positive, we were going positive x. We were traveling, if you were to draw it as an XY map, instead of a time position map, he was traveling along the x-axis one direction and then turned around. Okay, so let's do D. The velocity from 7 minus 4, that is a difference of 3 seconds, right? 4, 5, 6, 7, 3 seconds. At 7, we are at negative 5. Negative 5. At 4 seconds, we are at positive 5, minus 5, minus 5, minus 5. It's actually minus 10. Negative 10 over 3 is negative 3.33, I believe, repeating, meters per second. Last one. E. The velocity. So the total time, 8 seconds. 8 minus 0, 8. The total amount of time. The total distance. We were at 0, and we stopped at 0. So 0 minus 0 is 0. So our average velocity, 0 meters per second. So we can see why average velocities are not very helpful. An average velocity across a whole time span, if you go away from home and then you come back home, you could say that you didn't move at all. Your average was 0. So that's why in certain cases we want to know instantaneous velocities somewhere between the charts, not necessarily across 2 points. Okay, I'm going to call it. Turn that off. 4. An attacker at the base of a castle wall, 3.65 meters high, throws a rock straight up with a speed of 7.4 meters per second, at a height of 1.55 meters above the ground. A. Will the rock reach the top of the wall? B. If so, what is the speed at that moment? C. Find the change in speed when throwing down between those same 2 points. And D. Does the change in speed agree in magnitude between going up or going down? So we need to start with A, obviously. Will the rock reach the top of the wall? What are we given? We are given that the wall is 3.65 meters high. So if we draw our little picture, draw a little stick man here, castle wall. The ball starts above the ground at a height of 1.555 meters. And he throws it straight up with a velocity of 7.4 meters per second. The height of this wall, 3.65. So let's also get our initial height. Y initial is 1.55 meters. Our initial velocity, 7.40 meters per second. We also know about gravity, negative 9.80 meters per second squared. These are positives because that's going up. He's positive because he's not in the ground. Positive because he's not in the ground. So this is what we get. We need an equation. Where's my... Okay, so what are we missing? We are missing the final velocity and let's write it like this. Missing. We are missing the final velocity, the final height, and the amount of time. So we need an equation that has these and has these. We have one equation that really does the trick here. I'm going to get rid of the picture just so we have room. The one that does our trick here, our equation, be y equals, that's the final height, 1/2 at squared plus VOT plus YO. We can plug in most of these values. We get y equals, A is 9.8, half of that, negative 4.9 t squared plus, because we're going up, 7.4 t plus the initial height, 1.55. We also have an equation that we can use here, which is our velocity equals the acceleration plus VO. That's our gravity again. That's our initial velocity, so we can plug those in. Negative 9.8 t plus 7.40. It's just 0. So, how do we solve this? We need to consider what happens when you throw a rock straight up. When you throw the object straight up, it'll come up to the top, stop, and then fall back down. If you did that on a timeline, such that this is time, I'm just facing the wrong direction, time, it would reach a height at a certain point, and then at a certain point come back down. And so there's this moment at the very top when the slope, the instantaneous velocity, is 0. When the instantaneous velocity is 0, that is when this value here is 0. So if we plug a 0 in right here, we can solve for the amount of time it took to get there. So let's do that. Let's just clean the spot up here. So we get t equals, move that negative 7.4 to the other side. Divide both sides by negative 9.80. Those cancel. It's positive now. Positive time is good. 7.4 divided by 9.8 gets us a value of 0.755 seconds. So this was in meters per second over meters per second squared. The second drops on the top. The second on the top comes to the top. M's cancel. One S on the bottom cancels. We're left with S on the top. Seconds. So it'll take 0.755 seconds to reach the point when the velocity becomes 0, which will be at the highest point of the throw. Therefore, when the time reaches 7.5, we are at our highest height. We plug in 0.755 into these t's, and we will find what the highest point the rock hit was. So, the final height will be negative 4.9 times 0.755 plus 7.4, that's squared, times 0.755, not squared, plus 1.55. This gets us a value of about, make that better, 4.3438775 meters. We round for significant figures, so 4.34 meters. 4.3, here, let's breathe that cleaner. 4.34 meters. A. Will the rock reach the top of the wall? The highest that the rock will move up to is 4.34 meters. The wall, say if this is the height of 4.3, down here obviously is like 3.6. So yes, the rock will go higher than the wall. If so, what is the speed at that moment? Okay, so we flip this. We had an initial velocity at 0 when it got to the top, but we're not at the top now. We're still moving up. So we instead flip these values so that we can find the time here. So we can go the final height of the wall minus the initial height equals 1/2 at squared plus velocity, initial velocity times time. We want to solve for t in this case. We're going to plug in all of our values first. So 3.65 minus 1.55, negative 4.9 t squared plus 7.4 t. That gets us, put a 0 there, negative 4.9 t squared plus 7.4 t. This will be a positive on this side, so it's going to be minus 3.65 minus 1.55 gets us 2.1. This can be, you can find the t here using the quadratic equation, which is b squared, negative b squared, plus or minus the square root of b, no, to solve this, we can use the quadratic equation, which states that t will equal negative b plus or minus the square root of b squared minus 4ac all over 2a. The b term is 7.4, a is negative 4.9, c is negative 21, so it's a, b, c. You plug those values into t here in the quadratic equation, and we get that time has, there'll be two answers. One where you go negative b plus that, one where you go negative b minus that. So you get two answers. In this case, we get the answer of, and it makes sense, there should be two answers, right? It hits that point twice. And our two answers are 0.378 seconds, and the other one is 1.13 seconds, which obviously the lesser known time and the greater time. So on its way up, it reached the wall's height at 0.378 seconds. Plug this number now in to this. Final velocity equals negative 9.8 times 0.378 plus initial velocity 7.4. So our velocity when the rock reaches the top of the wall will be approximately plus 3.6858 meters per second. So plus 3.69 meters per second. Okay, so that solves A and B. A, will the rock reach the top of the wall? Yes. If so, what is the speed at that moment? The speed, the velocity equals 3.69 meters per second. C. Find the change in speed when throwing down between those same points. So we can just flip our equations. We had the final velocity is AT plus initial velocity. So in this case, our initial velocity, previously we said positive 7.40 meters per second, but we're throwing down, which means it is now a negative sign. So V equals negative 9.8 T minus 7.40 meters per second. That's our new equation. Likewise, for our height, our final 1/2 AT squared plus VOT plus initial height. The initial height now is actually at the top of the wall. 3.65 meters high. And the bottom is 1.55. Because those are our 2 points. We flipped everything. So we move this to the other side. 0 equals 1/2 AT squared plus initial velocity squared plus 21. Again, we do the quadratic equation to solve for t. So A term, B term, C term, that's negative 4.9. That's negative 7.4, and that's plus 20, or plus 2.1. We plug those into the quadratic equation, and we get, again, 2 answers for t. One of them, however, is a negative value. One of them is negative 1.75. The other is a positive value at 0.24426. Let's just say 0.244. This is in seconds, or in time. First one doesn't work. No such thing as negative time. So clearly, there's only one time that shows up, the positive one. So this is the time it takes for the ball, or for the rock, to reach the ground from the castle wall. So we plug this value in to V to find what its velocity was. So V equals negative 9.8 times 0.244 minus, because our initial velocity is going downwards, 7.4. So our velocity when thrown downward will be negative 9.79 meters per second. Find the change in speed when throwing down versus throwing up. So the change in speed, let's say delta V, one of them is 9.79. The other one was 3.69. So throwing down versus throwing up. That is a difference of 6.1 meters per second. D. Does the change in speed agree in magnitude between up and down? Why? we throw up, the rock started at 7.4, and when it reached the top, it was at 3.9 or 3.69. When we throw the ball down, it starts at 7.4 and ends at 9.79. The difference between these being 6.1 meters per second. Does the magnitude make sense? We say, yes, it does. Why? Well, gravity is aiding the rock as it falls, whereas when it goes up, gravity is fighting the rock. How much does it fight the rock by? It fights it by a constant negative 9.8 meters per second squared. So after about 1 second, a change of speed will be to about 9.8. From here to here was about 0.2 of a second. And we increased speed by about, let's get a calculator. .79 divided by 7.4. Let's go 7.4 divided by 9.79. It's about 75%. 75% of 9.8. None of that matters. Whatever. So gravity is accelerating it by that much, and it's also hindering it by about that much. In fact, going up, it took what? 3 seconds? 0.3 seconds? So we can see here that the shift is approximately within the magnitude of the gravitational acceleration within a second. So I would say, absolutely, yes it does. Okay. Go. Pause.